In the previous video, we derived the integrated rate law equations for the 0, first, and second order cases. In this video, we see how these equations can be practically used with real chemical reactions. This table shows a summary of the rate laws and integrated rate law relationships for the 0, first, and second order reactions. We can use the integrated rate laws in one of two ways. We can use real experimental rate data to determine the order of reaction by plotting the relevant data to see if we can obtain a straight line relationship. Or, if we already have information about the rate constant and rate order, we can use the relevant integrated rate law to determine a variety of parameters, including the concentration of a reactant at any time during a reaction, or to determine the time a reaction will take for the reactant to fall to a specific concentration value. We will have a quick look at both examples now. Starting with determining the order of reaction. To determine the order of reaction from experimental rate data, we will use the decomposition of nitrogen dioxide as an example. This table shows a real data set for how the concentration of the reactant NO2 decreases with time at a particular temperature. We can plot this decrease in reactant concentration with time, and we can see from the slope of the curve that the reaction rate is relatively quick at the beginning and slows as the reaction proceeds, and this is typical for most reactions. Now, if this reaction happened to be zero order with respect to NO2, we would expect a plot of concentration versus time, like this graph here, to be linear. The fact that the plot shown is not linear tells us that this reaction is not a zero order reaction. Now, if the reaction was first order with respect to NO2, then we would expect a straight line plot when we plot the natural log of NO2 concentration versus time. So we can take the natural log of the NO2 concentration values and place them in our table. And we can plot the log data versus time. But again, we see that the resultant plot is not linear. This indicates that this reaction is not first order with respect to NO2. Now, if the reaction happened to be second order with respect to NO2, then we would expect a straight line plot when we plot the inverse of NO2 concentration versus time, and that the slope of this straight line plot would be equal to the rate constant K. So we can take the inverse of the NO2 concentration values and place them in our table. This time, when we plot 1 over the concentration of NO2 versus time, we see that we get a straight line. And this indicates that this reaction is in fact second order with respect to NO2. We can determine the slope of this curve by calculating rise over run, where we get 5.26 minus 2.00 divided by 300 minus 0 to get a slope of 1.09 times 10 to the minus 2 molarity to the minus 1 seconds to the minus 1. And this is the value of the second order rate constant for this reaction at the particular temperature that the experiment was carried out. We can now write a rate law for this reaction as rate equals the rate constant K times the concentration of NO2 raised to the power of 2, since we have determined experimentally that the reaction is second order with respect to NO2, and we have even calculated a value for the rate constant for the reaction based on the slope of the straight line curve. The second way to use the integrated rate laws is to use them to determine some very specific reaction parameters, such as the concentration of a reactant after a given time, or the length of time it will take for a reactant to drop to a certain concentration value. And both types of calculations are very useful in real-world applications. We'll use the decomposition of dimethyl ether as an example. Now, this reaction happens to be a first order reaction with a rate constant K of 6.8 times 10 to the minus 4 seconds to the minus 1 at 510 degrees Celsius. And note how the units for the rate constant, seconds to the minus 1, match that expected for a first order process. A typical problem we'll want to solve may look something like this. If the initial concentration of dimethyl ether is 5.00 molar, A, what is the concentration after 30 minutes? And B, how long will it take for the concentration to drop to 3.50 molar? Given that we have a first order process, we will use the first order integrated rate equation, and we can now substitute in the real reactant terms, being dimethyl ether, or CH3,2O. To answer part A, we note that the reaction time is 30 minutes, which equates to 1800 seconds. The value of the rate constant is 6.8 times 10 to the negative 4 seconds to the minus 1. The initial reactant concentration is 5.00 molar, and the concentration of the reactant after 1800 seconds is the quantity we've been asked to calculate. Substituting these values into the equation above, we get this equation here where we see that the natural log of the dimethyl ether concentration is 0.385. Solving for concentration by calculating e to the power of 0.385, we get 1.47 molar, or 1.47 moles per litre. So in other words, after 30 minutes of reaction, the concentration has fallen from 5.00 molar to 1.47 molar. A very useful type of calculation to be able to do. To answer part B, how long will it take for the concentration of dimethyl ether to drop to 3.50 molar? We use the same first order rate equation, and note that in this case the time of reaction is actually the experimental parameter that we are being asked to calculate. K is again given as 6.8 times 10 to the negative 4 seconds to the minus 1. The initial concentration is again 5.00 molar, and the final concentration at time t is given as 3.50 molar. Substituting in the relevant values, we get this expression here, which can be rearranged to make t the subject of the equation, and when we solve for t, we find that it will take 525 seconds, or 8.74 minutes, for the reactant concentration to drop from 5.00 molar to 3.50 molar. Again, a very useful type of calculation to be able to carry out in real-world applications.